All right, time for another video. Here we go again. I'm doing a series called The Impossible Mathematics of Atheistic Materialism and Evolution. And I'm on what I call the probability problem. And in this particular video, I'm doing a comments on the second part. So you're getting ready. Well, hopefully, anyway. I'm just trying to make a joke out of it. The spin zone by my opponents. They talk about how, RNA, it's a self-replicating molecule. It can make copies of itself, etc. And at least I'll give them credit. They said imperfectly. So my question, though, and it still is, well, by how much? Give me a percentage. Is it, like it can copy 99.9% and 97%, 85%, 45%? What is it? What's the percentage that it can copy? So that's what I want to know. So without further ado, let's watch a video clip.
And if you happen to get a strand of RNA that happens to code for something, just by happenstance, it happens to code for the production of a certain enzyme, how do you make another one of those RNAs? Replicating that is very hard. And people will say, well, that first strand replicates a second strand, and each of those act as a mother toward replicating daughter strands. The problem with that is that so far, no one's ever gotten RNA to duplicate itself. Gerald Joyce has tried, very sophisticated trying. I mean, the guy's a master with this stuff. I don't know RNA like he does. And he, with all of his design, has only been able to replicate about 10% of the RNA. So 10% of a replication is not a replication, not at all. And that 10% is too short to act as a replicator itself. So those.
Okay, so the presenter is talking about a strand of RNA that can code for an enzyme, or what we would consider a molecular machine. And then he gave me a name, Gerald Joyce, and so I'm going to show you a video here in a minute from Gerald Joyce, and they're going to talk about an enzyme as well, or again, a specific molecular machine. RNA, so far, from what the presenter said, can replicate about 10%. Okay, 10% from a masterclass chemist run by Gerald Joyce. All right. So what still bothers me, and it still isn't really ever covered, so that, say, a replicator can replicate something, it doesn't tell you where the code comes from. It does not tell you where the code for what it's replicating comes from. Where does the code come from? And we're going to talk about that more as we get into the video. So let's watch the video from Gerald Joyce himself.
So this now optimized molecule can, to some extent, copy the copy. So this, everyone knows, I think, what PCR is, polymerase chain reaction. You would start with a template. You would bind a primer to the template. Only in this case, the template is RNA. The primer is RNA, the building blocks are RNA, the RNA NTPs, and the enzyme is RNA. So the RNA enzyme extends this primer on the template, and then that product binds a reciprocal primer, which the RNA enzyme extends and makes copies of the copies. We call this ribo-PCR, right? This is the PCR of the RNA world. Now, of course, there is a DNA-based human that is squirting things into the test tube, and there is a thermal cycler machine that we bought that was made by DNA-based humans. But once the reaction is running, it contains just RNA enzymes, RNA building blocks, a little RNA template starting material, RNA primers, and magnesium salt. And it just runs, just like PCR, only this is ribo-PCR. So it's not as efficient as good old PCR in a thermal cycling type environment. And Jack Shostak talked yesterday about imagining thermal cycles where in the cooler temperature, the primer is extended. In the warmer temperatures, they're separated. 1 makes 2, makes 4, makes 8, and so on. So that's ribo-PCR. But the fact is, this process is not yet good enough that we can do ribo-PCR of the enzyme that does ribo-PCR. If we did that, we would really be in good shape, right? Because then you would have a general purpose, self-sustained, evolving molecule. It can make pretty good sized segments, but the longer the piece, the more structure, there's a couple sequences that are more difficult. It can't make something as big as itself. So that's kind of where things are now. We, of course, want to get to the point where it can make itself, the polymerase, not just the ligase, and maybe not the whole polymerase, but the fragments that can assemble to be the polymerase. So let me come back and end with the timeline again. Remember, we are here. We used to be here, we think. It is a hypothesis, though. Let's be careful, right? There's no direct proof that life on Earth came from RNA. There's a lot of indirect evidence to suggest that was the case, but there's no direct proof. It is a hypothesis.
Okay, so here you have, again, a master class chemist in a master class lab with master class associates, and in the full video he shows you his associates at the end of the video. They design a, quote, optimized molecule or a designer molecule, a manufactured enzyme or a molecular machine that they program or they set it up to do a particular thing. So they have actual human involvement. Translation. It was designed by brains to do a specific task. It was set up also in a pure RNA world, using RNA purchased from the natural world. So you have to ask yourself, I'm sorry, but where on the early Earth did this pure RNA world ever exist? Which also means we get all of our molecules from nature, but purified, by labs and everything. So you have in the video, the longer version, they talked about test tube evolution. He goes over test tube evolution. Well, what is test tube evolution? It isn't evolution. It is not origin of life evolution. It is test tube. It is humans. It is lab involvement. It is a misnomer, and I'm sorry, but that's a lie to say something like that. And it is not directed evolution. There's no such thing as directed evolution. We're trying to come up with a purely naturalistic way of getting this stuff, but you have test tube evolution and directed evolution. That's creationism in a test tube with actual purchased machines involved as well, not only humans. So why do they call this evolution? Because they have to. But this isn't Darwinian evolution. So if Gerald Joyce had took his lab RNA World and put it into an early Earth environment, how long would it last? It wouldn't last 2 seconds. And of course, he's going to put a happy face on his work. He actually believes that the RNA world might be the answer. But of course, I'm glad he's at least willing to say, look, it's just a hypothesis. So, I agree. And guys, I have sympathy. I'm not totally ignorant. I do have sympathy for people that are working a lifetime on this stuff. I do, okay? But where's the full, open, honest discussion about this stuff? Just because you can, and they haven't gotten there yet, just because you can make a copy of a copy, that means nothing. That means nothing, okay? So I'm going to give you a rundown. So he started out with an optimized molecule. That's a designer molecule. And he said to some extent. What does some extent mean? It can copy the copy. What does some extent mean? Then he has an RNA template. Of course, it's made out of an RNA primer. And then he has the other building blocks of RNA. And then he has an enzyme, which again is a molecular machine. Then an RNA enzyme extends the primer on the RNA template, and then that product combines to create a reciprocal primer. But you have a human involved, and you have a machine involved that they bought. So excuse me, how does this have anything to do with early Earth accidentally setting all of this up and keeping it going? Then he says, okay, once we have the reaction running, then all you need is, you need RNA enzymes now, RNA building blocks, you need a little RNA template material, you need RNA primers, you need magnesium salt, and then he talks about, okay, now let's leave the lab temporarily, children, class, put your thinking cap on, because you heard another lecture yesterday where someone mused that you had these hot and dry cycles. I've heard this a gazillion times now since I've been doing this, a gazillion times about these hot and dry cycles. And then we come back to the lab, and then he says, but here's the problem. We don't get a full copy of even the enzyme. We don't get ribo-PCR of the enzyme that does the ribo-PCR. So wait a minute, I want to scratch my head, and I want to, raise my hand. You mean we can't even replicate one enzyme yet? So he said, of course, if we could, you'd have a general purpose, self-sustaining, evolving molecule. If you could. So he also said it can make pretty good segments. What does that mean? It can replicate pretty good segments. What does that mean? You can replicate pretty good segments. How much is pretty good? It can't make something as big as itself. It cannot make an enzyme. So we're not even to an enzyme yet in this RNA world hypothesis. So the video also talked about an RNA polymerase. And again, I'm just talking about in a standard cell. In a standard cell, the RNA polymerase is a molecular machine. What does it do? Well, it transcribes the genetic information stored in the DNA to an RNA. That's what it does. But even that cannot replicate itself. I mean, here's the polymerase in charge of building the actual RNA molecule in a normal cell, and it can't replicate itself. Okay. In fact, it can't even replicate itself. And in the video, he talked about how they could take their designed polymerase, bust it into 4 different pieces, and as long as each piece was near each other, they could also do replication. Not as well as when it was together, but still it could do replication. So he was saying that, well, maybe we can get it to do, the 4 pieces, whatever. So even using designer molecules, designer enzymes controlled by human involvement and machines, we can't even get an enzyme. One molecular machine. And all of this was done in a pristine lab using pristine chemicals in a pure RNA world that they designed. So there's not one shred of prebiotically relevant for early Earth chemistry here. Not one shred. Yet it was touted as, again, it was test tube evolution. Well, test tube evolution is not evolution. Not what we're talking about. And directed evolution is not the evolution we're trying to get a hold of here. And Gerald Joyce even admitted once again, there is no direct proof that the RNA world hypothesis is the route that it took. Okay? So Gerald Joyce's RNA world is a creation from a mind. His designer molecules with human involvement and machine involvement, a pristine lab and a pristine RNA, do not mirror early Earth. So please, I want you to get this. Listen, we need more than a simple copy machine. We're not talking about just an enzyme that can make a copy of itself. So you have one enzyme, mind you. We're not even there yet. We're not there yet. We can't even get one enzyme. And you're supposedly heading towards the building of life, the cell. Today we have 500 billion molecular machines in the tip of our finger. More machines in the tip of our finger, molecular machines, enzymes, in the tip of our finger than all the machines in the world combined. We have tens of thousands to 100,000s of them, of these different molecular machines, different kinds of them. But in 2023, we're not even to one enzyme, let alone the rest of the cell. Yet as he pointed out, we also need proteins and DNA on top of that, not just RNA. I'm telling you, that's something I've been trying to get across to the atheists this whole time, and all they do is stick to the RNA. They think that somehow, and I heard it in another video, that they think that they can bootstrap RNA all the way up to a cell. Nonsense. It's nonsense. And it's something I've been screaming ever since. Now, I'm going to end with this little video.
The RNA World Hypothesis.
RNA world is this idea that you can string together enough nucleotides to make a chain long enough to copy itself, and then, once copied, to do the same thing over again. Origin of life researchers imagine the very first life as being made of nothing but RNA, and that it could somehow bootstrap its way to a bigger world where there's protein and DNA.
If you just look at an RNA molecule, it seems to fall to pieces. Working with RNA is extraordinarily difficult because it's so delicate. It's meant to be a temporary store of information. And as a consequence of its delicacy, it's extraordinarily unlikely that it's going to be useful as some kind of starting point for life.
So RNA can't precede the first cell because it has to be enclosed in a cellular environment to be stable, to be copied, to be useful.
Today, RNA molecules are manufactured under laboratory conditions.
If you want to build RNA in the lab, you have to spray down your surfaces and wipe your pipettes and wear special gloves and keep it covered, and then hope that you don't get any contamination, because if you do, the RNA is gone. And then you have the sequencing problem to solve. So you need scientists working hard to sequence the RNA and try different combinations and find one that might copy itself. So you have to have a complicated string of RNA that can function both as the inheritance and the enzyme in the system. And it's the best minds in the world working on it, and they haven't succeeded in cracking the problem.
Reflecting on the origin of life and the implications of synthetic RNA, chemist Robert Shapiro noted, "The flaw with this kind of research is not the chemistry. The flaw is in the logic that the experimental control in a modern laboratory could have been available on the early Earth. In reality, the odds against RNA forming on its own are astronomical."
All right, enough said. Have a blessed day.